Welcome to Module 3, Thermodynamics for BAS Professionals. In this module, we are going to connect BAS data to the real physical system. A control sequence can open a valve, start a fan, or change a set point, but it cannot create or destroy energy. That is why thermodynamics matters in building automation. It helps you look at temperatures, flows, humidity, and power values and ask a very professional question. Does this story make physical sense? By the end of this module, you should be able to use conservation of energy to evaluate HVAC performance and identify BAS data that is physically inconsistent before you start changing logic. Think of this module as a field tool. We are not doing theory for theory's sake. We are learning how to protect equipment, avoid false conclusions, and make better decisions with evidence. Let's start with the learning objectives. After this module, you should be able to explain what conservation of energy means in HVAC systems. You should also be able to separate heat, work, temperature, power, and stored energy. You will use sensible and latent heat concepts to understand why a system may satisfy temperature while still failing humidity control. You will also apply mass and energy balances to compare airside and waterside performance. Most importantly, you will learn to recognize when BAS data is physically impossible, incomplete, or not trustworthy enough for a major decision. This is the mindset of a strong BAS professional. Do not just read the trend, test the story against the physics. Thermodynamics is not only something in an engineering textbook, it is happening every day in the mechanical room. A boiler converts fuel or electrical energy into thermal energy. A chiller uses work to move heat from a colder place to a warmer place. A cooling coil transfers heat from air into water or refrigerant. A humidifier adds water vapor and energy into an airstream. The BAS does not directly see all of this. It sees sensor values, commands, alarms, and trends. That means the BAS professional has to interpret those values carefully. When the BAS says the chilled water is 44 degrees, the valve is 100% open, and the supply air is still warm, we should not immediately blame the valve or the coil. First, we ask whether the measurements are plausible. Thermodynamics gives us a practical way to check that. The first law of thermodynamics tells us that energy is conserved. In simple field language, energy entering a system must either leave the system, become useful heating or cooling, be rejected somewhere else, or be stored temporarily in the building, water, metal, air, or equipment. Look at a cooling coil. Air passes across the coil and loses energy. Chilled water passes through the coil and gains energy. Under steady conditions, those two stories should be reasonably close after allowing for measurement uncertainty. If the airside calculation says the coil removes 300,000 BTU per hour, but the waterside calculation says 900,000, the coil did not break the law of physics. The data set is probably wrong or incomplete. Before changing control logic, verify that the measured values obey the physical system. Before calculating or troubleshooting, define the control volume. A control volume is the boundary around the system you are evaluating. It could be a cooling coil, an air handler, a chilled water loop, a chiller plant, or an entire building. This step matters because your answer depends on what crosses the boundary. If you are reviewing a cooling coil, you need air entering and leaving, water entering and leaving, flow rates, and the operating state. If you are reviewing a plant, you may need chillers, pumps, towers, and heat rejection. A common mistake is mixing boundaries. For example, comparing chiller compressor power against building cooling load while ignoring pumps and towers. In the field, sketch the boundary first. Then identify what energy enters, what energy leaves, what work is added, and what may be stored. Now, let's separate four terms that are often confused. Heat is energy transferred because of a temperature difference. Work is energy transferred through a mechanical or electrical process, such as compressor shaft work. Temperature describes thermal state, but it is not total heat content. Stored energy is the energy held in water, air, the building structure, furniture, equipment, and piping. This is why temperature alone does not describe load. A small metal part at 200 degrees may contain less total energy than a large tank of water at 80 degrees. For BAS troubleshooting, this is a big point. A high temperature does not automatically mean a high load. You must consider mass, flow, specific heat, and time. A good technician does not chase temperature alone. A good technician asks what energy is moving, where it is moving, and how fast it is moving. Sensible heat and latent heat are both important in HVAC. Sensible heat changes dry bulb temperature. For example, cooling air from 80 degrees to 60 degrees removes sensible heat. Latent heat changes moisture content or phase. When water vapor condenses on a cooling coil, latent heat is removed even though it does not show up only as a dry bulb temperature change. This explains a very common BAS problem. A space can be 72 degrees and still feel uncomfortable because humidity is too high. The sensible load may be satisfied, but the latent load is not. In a valve system, supply air temperature reset, low airflow, reheat, and coil leaving conditions can all affect humidity performance. So when there is a humidity complaint, do not only lower the room set point, evaluate the full sensible and latent process. Heat transfer rate depends on mass flow, specific heat, and temperature difference. For water, we often use the field formula Q equals 500 times GPM times delta T. That gives BTU per hour for water under common HVAC conditions. For air, we often use Q sensible equals 1.08 times CFM times delta T for standard air. These formulas are useful, but they are approximations. They assume typical water or standard air properties. Glycol concentration, altitude, temperature, humidity, and measurement uncertainty can change the result. The professional use of these formulas is not just to get a number. It is to test whether the number is reasonable. If a small coil is supposedly moving an impossible amount of energy, do not celebrate the calculation. Question the inputs, units, sensor scaling, and operating condition. Sometimes dry bulb temperature is not enough. That is where enthalpy becomes useful. For moist air, enthalpy represents total energy, including the sensible energy of dry air and the latent energy associated with water vapor. This matters for economizers, mixed air, cooling coils, and humidity control. Outdoor air may be cooler than return air, but if it contains much more moisture, it may carry more total energy. Temperature-only economizer logic can make a bad decision in humid weather. A BAS professional should know when to look at dew point or enthalpy instead of dry bulb temperature alone. For refrigeration systems, enthalpy differences help explain heat absorbed, work added, and heat rejected. The practical lesson is simple. When moisture or phase change matters, temperature alone is not the full story. Calculations are only as valid as the operating condition. A steady-state condition means the important values are not changing significantly with time. In that case, an energy balance is usually more reliable. A transient condition means the system is still storing or releasing energy. Think about morning warm-up, chiller startup, a large occupancy change, solar gain increasing during the day, or recovery after setback. During these conditions, the building mass, water, metal, and airstream may still be changing temperature. A coil or plant can appear out of balance because energy is being stored or released inside the boundary. So before you judge the numbers, ask, is the system stable enough for this calculation? If not, trend longer, wait for stabilization, or clearly state that the calculation is only a snapshot. Efficiency depends on the boundary you choose. Boiler efficiency compares useful heat output to energy input. Chiller or heat pump COP compares useful cooling or heating output to work input. Plant per ton can include chillers, pumps, towers, and related auxiliaries. That difference matters. A chiller can have a good per ton while the total plant performs poorly because pumps, cooling towers, or control strategy are wasting energy. The same is true for boilers. The boiler may be efficient on paper, but high return water temperature, short cycling, or poor distribution can reduce system performance. A BAS professional should always ask, am I measuring the equipment, the subsystem, or the whole plant? Equipment efficiency and system efficiency are not the same measurement. Let's use simple examples to check the energy story. For the heating water example, 180 GPM with a 20-degree temperature drop gives 1,800,000 BTU per hour. That is about 528 kilowatts thermal. For the airside example, 20,000 CFM with a 20-degree drop gives 432,000 BTU per hour, or 36 tons of sensible cooling. For the chiller example, 1,200 kilowatts of cooling divided by 240 kilowatts of electrical input gives a COP of 5. These calculations are not just math exercises. They are quality checks. Always ask, are the flows actually measured? Are they estimated? Were they copied from design? Are the sensors calibrated? Are the units correct? The calculation is only as trustworthy as the evidence behind it. Here is a field scenario that every BAS professional should remember. A site reports that a cooling coil removes 900,000 BTU per hour on the water side, but only 300,000 BTU per hour on the air side. The first reaction is to blame the coil. Maybe it is fouled. Maybe the valve is bad. Maybe airflow is wrong. But the energy balance tells us something more important. The data set cannot be trusted as presented. In this case, the airflow came from a design document instead of a current measurement, and the water flow meter was incorrectly scaled. Once both inputs were corrected, the two estimates moved much closer together. Energy balance does not always prove which sensor is wrong, but it does tell you when the story is impossible. Let's review the common mistakes. The first mistake is treating temperature as total energy. It is not. The second is ignoring latent load, especially in humid buildings. Another common mistake is applying steady-state equations during startup or recovery when the system is still changing. We also need to avoid comparing equipment efficiency with plant efficiency. A chiller, boiler, fan, or pump may look good by itself, while the system around it wastes energy. Using design flow as measured flow is another major source of false conclusions. Design documents are not live measurements. Finally, never report an energy balance without acknowledging uncertainty. Airflow, water flow, humidity, and temperature measurements all have limits. Professional BAS work rewards evidence quality, not just fast intervention. Now let's apply the lesson. A BAS trend shows that a cooling coil removes 900,000 BTU per hour on the water side and 300,000 BTU per hour on the air side. The operator wants to replace the coil. What should you do next? The best answer is C. Verify airflow, water flow, temperature sensors, humidity data, units, and operating state. Why? Because the two energy estimates are too far apart. Replacing the coil before verifying the evidence could waste money and leave the real problem in place. Answer A moves too fast. Answer B changes a set point without diagnosis. Answer D hides the problem. The professional response is to test the evidence first, then decide the corrective action. For the practical assignment, choose one real or sample system, an AHU, coil, chiller, heat pump, or heating water loop. Define the control volume. Collect the required measurements. Preserve the units. Perform one energy balance calculation. Then identify the weakest assumption. Your deliverables should include a problem statement, a control volume sketch, input values with units, the calculation, a reasonableness check, missing evidence, and a recommended corrective action. The key takeaways are this. Energy is conserved. Temperature is not total energy. Sensible and latent loads both matter. Equipment efficiency is not plant efficiency. And impossible data deserves investigation before action. In the next module, we will build on this foundation by studying heat transfer and building energy balance.